So we are at day 5 today. So what did we see in the last class? The first thing that we saw was what are independent and what are dependent variables. Okay, independent variables and dependent variable. So your business will decide what is your dependent variable and what are your independent variables. Okay, so whatever is your parameter of interest for your business. So for a bank it can be whether a customer defaults or not, or it can be the revenue of the bank, the uh, sales volume of the bank, and so on. So that will be whatever is your variable of interest, it will be your dependent variable, and all other variables that you think is related to that dependent variable will be your independent variables. Okay, so dependent variable, and we will get something like this. This will be your dependent variable, and these are all your independent variables. So now you can include everything here. Whatever else you have, whatever other parameters you have, you can include everything here, even if it is not helping you find y, or even if it is not influencing your y, you can still have it here. Later the model will decide. If let's say x6, if this variable is not important for y, you will get 0 into x6. The model will automatically give that. The model should automatically give you that. Okay, so that we will see later. But this is what we saw, what are independent variables and what are dependent variables. The other classification that we saw was that of numerical variables or quantitative variables, and on the other side we saw qualitative variables. Okay, so this is quantitative and this is qualitative or categorical. Within quantitative we saw mostly two types, continuous and the other is discrete. Okay, continuous can take any decimal values. Between two continuous numbers there can be infinite number of other continuous number. Okay, so I can write 1.0 and 2.0. Now between these two I can have infinite numbers. I can have 1.01, 1.001 and so on. So this is a continuous number. Discrete on the other hand will take only whole numbers. Okay, so these are discrete numbers. Similarly on the categorical side we again had two parts. One was nominal, the other was ordinal. Okay, ordinal, as the name suggests, has an intrinsic order in the categories. So for example, low, medium, height. Okay, nominal on the other hand has no particular category. So colors can be nominal, red, blue, green. Okay, so this is the broad classification of variables that we saw. What else? Okay, we saw the concept of joins. We saw what are joins in R. I think I don't need to go into the details of it, but we saw what is a outer join. So if I represent it as a Venn diagram, if these are your two tables A and B, your inner join will be the intersection of the two. Okay, your inner join will be this particular portion. Your outer join will be the entire thing. Okay, then your right join will be this portion, and finally your left join will be the left side one. Okay, So I hope everybody understands that, and I don't have to go into the details again. We saw it in details in the last class. The syntax for that is merge. We use the merge function for it. So merge, we write by.x, we write the name of the column on the basis of which we want to join on the left hand side. So the first table's column. Okay. Similarly, we write the other table's column. So by.x the column name, by.y the column name, and then you write all.x is equal to true if you want to do a left join. You write all.y is equal to true if you want to do a right join, and you just write all is equal to true if you want to do a outer join. Okay, and by default it does a inner join. So that's how the syntax is. Okay, now moving ahead from joins. Then we saw a few important functions in R. Okay, we saw what is a scatter plot. Scatter plot is a normal two-dimensional plot between two variables. Okay, you represent it by the coordinates of the point. So you need to have two continuous variables to draw a scatter plot, or it can be drawn between discrete variables also. So scatter plot is always between numerical variables. Just remember that. Okay, because we need to have coordinates. Categorical variable will not have coordinates, right? Male does not have a coordinate. So it has to be either discrete or continuous. It cannot be a qualitative variable to draw a scatter plot. Okay, then we saw a few important functions in R. We saw the apply family of functions. First we saw what is the apply function. We saw T apply, we saw L apply, and we saw S apply, and we saw a few examples of where they are most popularly used. Okay, so apply function, the syntax is you take the object, you write 1 and 2, and then whatever operation you want to do. This is the syntax. T apply, it also takes 3 inputs. The second input is a category, is a categorical variable based on which your data will be divided. Then this is again some operation. So your data will be divided based on your second input, and your operation will be done on your first input. So this can be another column. So it can be another column of your data. Okay. Both lapply and sapply have similar syntaxes. The output of lapply is a list, and the output of sapply is a normal vector. The syntax is same. You write the object, and then you write the operation that you want to do. Okay, this is the syntax of lapply and sapply. We saw a few examples. I won't go into the details again. Okay. We saw how to write our own functions in R. So you give the name of the function, and then you write the keyword function. Then you give whatever inputs. If your function has some inputs, you can write those inputs here, and then within curly braces you can do whatever operation you want the function to do. Okay, at the end you can have the return. So you can return some variable here. So this variable var will be the output of this function, and whenever you have to call this function, let's say you have written a function here and you want to call that function now, so you can call it using name and by giving the inputs. So this has, so let's say it is taking 3 inputs, so you will have to give 3 inputs here. So let's say 2, 5, 7. Okay, and the output that you will get will be the value of that variable, whatever operation you have done on that. Okay, Yeah, we saw a few other functions. We saw the paste function, which is used to combine two strings based on a separator. Okay, so you give a separator, based on that separator you can combine them together. So we use paste for that. Percent in is used when you want to search a particular item in a list or in a vector. Then we use the percent in. grep, again, if you want to do a pattern matching, we use grep function. String split is used when you want to split a string, again based on a certain key. So let's say the employee id in some company is represented as a pipe operator. So you have some common code. So let's say 400 code, then let's say 301. So let's say this is the employee, this is the actual employee id, and this is the department number of that employee. Now you have to split them, then you can use the string split function. Okay, string split, then whatever this is you write that, and you give a separator, that the separator is your pipe operator. Okay, and then you give fixed is equal to true. So what this will do is this will give you 400 and 301 separately, which you can again use. So for that we use the string split function. Yeah, I think that is all that we covered, right guys? That's all that we covered. Any specific doubts if you have? Any question from the homework which you are not comfortable with? Yes, guys, can you hear me? Are you following? Neha has asked a question. X is sample of. Okay, gmat is matrix this. Okay, sure. So what the first line, what is it doing? X is equal to sample 0 to 999 250 replace is equal to true. Okay, now what does this mean? So sample function, we saw it in the last class. Okay, sample function does not generate random number. Okay, sample does not produce random number. Sample, what do you mean by sample? The English word sample also means sample means a sample, right? It's so simple that I'm not getting another word for it. So it's a sample. So you have a population, from there you take a sample. Okay, this is what it means. So what do you need to take a sample? You need the population, right? Only then you can take a sample from the population. So your population is this in this case. Whatever first input you provide, that becomes your population. So your sample is your population is all numbers from 0 till 999. From 0 till 999, all the numbers are your population. Now, how will you take a sample? You need to first define how many data points do you want in your sample. So I have given that here. I want 250 points in my sample. Okay. I want 250 points from this sample. Now what does replace is equal to true means? So there can be two ways of picking points from a population. One way is you just pick the point and you don't pick it again. Okay, you don't pick that point again. The other is you can replace the point and then pick again. So if you write replace is equal to true, the same number might come again. Okay, if you don't write replace is equal to true, the same number will not repeat. So let's give you a small example. So I have just 5 numbers. Okay, and then I take a sample of 3, let's say. So I will write sample 1 is to 5 comma 3. So these 3 numbers can be 2 3 1, let's say. Okay, now here I have given replace is equal to false, so I will not get a repetition. If I give replace is equal to true, I might get 1 2 and again 1, because I gave replace is equal to true. So the same number might be repeated, again might be repeated. It is totally based on chance. Okay, each number will have a equal probability of coming. So any one of them can come. So this is what is done using the sample function. Okay, and your other question is matrix sample 10, size 60, number of rows is 6. I think that would be sample 1 is to 10, right? Neha, are you sure the second one you have written it correct? So sample, if you just give 10, that means your population has only 10. So you will have 60 tens selected. Okay. You will have 60 tens selected, and then you are trying to form a matrix of them with number of rows is 6. So you will have 6 rows and you will have 10 columns. Since you have given size is 60, and all of them will be filled by 10. All will be filled by 10. Okay, this is what it means. Okay, all of them will be filled by the same number 10 because you are sampling from a population of 10. What are you getting when you run this? Okay, let me run it. Just a moment. Let me run it myself. Okay. So you can run it in two pieces. So first run whatever you have inside the bracket. So this should be n row. Okay, not nr. This should be n row. So this is what you have. Let me run only the sample function first. So I will run sample 10, 60 and replace is equal to true. Okay. Oh, this is strange. It is giving you. Okay. Uh, I think what's going on here is it is taking 1 to 10. It is taking 1 to 10. So I guess if you give just 10, it assumes that you want to go from 1 till 10, not just 10. Okay. So it is equivalent to giving this. It is strange, it should not happen, but that's what it assumes because you have given only one number. So R assumes that your population cannot be just one number. So it starts from 1 basically. Okay. So this is what your sample function will give. And when you write matrix on top of it, then it will just create a matrix out of those random numbers. Okay. Why? No, are you asking sample is greater than population? No, no, no. You have given replace is equal to true. So it will become greater than population. Okay. Because you have given replace is equal to true. So imagine this situation. I give only two numbers, 1 and 2. Okay. And I give a size of 60. So even in this case, you will get 60 ones and twos picked randomly. So here also your sample is greater than your population because that's what you have given as input. Yeah, why would we take such example? That makes sense. We never do that, but since it was asked, we are doing it. But we never do that because your population will never be uh, smaller than your sample. Neha, is your doubt clear now? No. Okay, I'm not sure. No, no, Neha, when replace is equal to true, what happens is, what if we replace. No, no, replace is okay. Let me explain it once again, guys. So your population is like a big bag. Okay, your population is like a big bag which will have some numbers, whatever you give. Okay, so if you give 1:10, your population will have, let's say, 10 marbles. It will have each with one number. So when you give your population as 1 to 10, imagine a big bag which has many marbles, each with numbers 1 till 10 written on it. Okay, now when you give, let's say, to sample, you give size of 5. Okay, and you give replace is false. Okay, when you give replace as false, what happens is you will pick 5 marbles from this bag, the bag of your population. You will pick 5 marbles from here, and once you pick a marble, you don't replace it back in the bag. So your 5 marbles may be, let's say, 1, 9, 10, 3 and 5. These are the 5 marbles that you picked. You will not get the same number again, because once you picked a marble, it's gone out of the bag, so you will not get the same marble again. Okay, now let's say you pick 5 numbers and you give replace is equal to true. So now what you will do, you will put your hand inside, you will pick one marble. Okay, let's say you got a marble with 1, with number 1 on it. Okay, now what you will do, you will just make a note of it, and then you will replace the marble back in the bag. Okay, you will replace the marble back in the bag, and then you will pick again. So again there is another 1 in your bag, and so it might come again in your pick. Yes, exactly, Saraswati, that is right. If you write something like this, if you write sample, let's say 1:10, and you give a size of 60 with replace is equal to false, you will get an error, because with replace is equal to false, it cannot pick a sample of 60 from 10 population. This is the error. It can only pick max of 10, not more than 10, because after 10 your bag will be empty. After 10 your bag will be empty. Nothing will remain in your bag if you give replace is false. Okay, so for example, if I give 2 here, the answer will be 1 and 2, because there are only 2 marbles in your bag, one with number 1, one with number 2. The moment I make it 3, it will give me an error. Okay, replace is true. So let me make replace is false. So size 2 will work perfectly. It will give me 2 numbers, 1 and 2. The moment when I make size 3, it will give me error. See, cannot take a sample larger than the population when replace is false. Okay, so it is telling you exactly the error. It cannot take a sample larger than the population when your replace is false. So your replace has to be true. And once you give a replace to true, you can take any number you want. You can take 30 also. It will just keep repeating the same numbers. So now is that clear, Neha? Why is it generating the value? So that's what I told you, right? Because your replace is true here, so it can take 60 values out, because you have given replace is equal to true. Okay, and this is not 10, this means 1 till 10. Okay, the moment you give just one number, it means 1 till 10. Okay, so when you run gmat, you will get a matrix of all numbers randomly picked between 1 to 10. So this is equivalent to giving 1:10 here. So these two are equivalent. Again, I have not set a seed, so I will get different answer every time I run. Okay, okay, the seed function. Okay, set.seed, let's say I give some constant 1. Okay, I give any constant 1. The constant is irrelevant, you can give any constant. Okay, so I have given set.seed 1. Now let's say I will take a random sample from 1 till 10. Okay, and I'll give size is equal to 4. So I set a seed and then I run this. What do I get? I get 3, 4, 6 and 10. Okay, now let's say I run the same function again. I run the same command, same line again. Now you see I'm getting a different answer. I'm getting a different answer. I got 3, 9, 10 and 7. Okay, I did not get the same answer again. But now let me run it once again. Now once again I will run it again by setting the seed as 1. So again I set the seed as 1 and then again I run it. You see I got the same answer as I had gotten the first time. 3, 4, 6 and 10. Again here also 3, 4, 6 and 10. So what does it mean? This means that every time you set your seed and you run some command which involves random numbers, the random numbers generated will be the same random numbers. If you don't set the seed, you will get a different piece of random number. Okay. So now let's say if you run the command on your system and if you set a seed of 1, even you will get the same answer as I have got here. But if you give a different number, you will get a different answer. 1 is just a constant, Neha. You can give any number. Let's say I give 100 or I give 10,000. Okay. I give 10,000 and I run it. So I get 5547. Okay. I again run this same command again along with the seed. Along with the seed I am running it again. Again I get 5547. So it just means that it should be a constant k. It can be any constant, any number you want. Okay. So just to avoid writing a bigger number, we write 1. Because writing 10,000 it requires more effort than writing just 1. It should be any constant. Okay. Pankaj, is that clear now? What is happening if we make a seed of 10,000 or any big number instead of 1? Neha, any software that you use, it generates random number using some algorithm. Okay, internally some algorithm runs and it generates random numbers. So whenever you give a constant, that process it becomes defined. It follows the same process every time. Okay, so whenever you give any constant number, it will follow that same process to find the random numbers. Okay, now what that process is, we don't need to know that. It just means that it will follow the same process again and you will get the same answer. So let's say if I have to tell you that this is how R generates random numbers. Okay, so let's say the moment you give your command here, so these are the different ways R can generate random numbers. Okay, so these are the different ways you get the random numbers at the end of the this line. At the end you get here random numbers. So the moment you set a constant, so let's say k is equal to 1, that 1 represents, let's say, this line. This particular branch is represented by k is equal to 1. So every time you give k is equal to 1, it will follow the same step. It will follow this line and it will give you the same random number again and again. You give a different constant, it will go to a different line. Let's say this is k is equal to 5. So when you give k is equal to 5, it will always follow this branch and it will give you these random numbers. Okay, so which constant you follow is not important. The only thing that is important is it should be the same constant every time. Okay, for the same operation. Yes, Pankaj, that is correct. Set seed 1 and set seed 2 will have different output, but will generate same random numbers for every x. Yes, exactly. So if you run set.seed with 1, let's say you get 5, 4 and 3. Okay, if you run set.seed 2, you will get some other random number, let's say 1, 3 and 5. Okay, but every time you run this code, you will get the same 3 random numbers. Every time you run this code, you will get the same 1, 3 and 5 every time. Okay, clear guys? Set.seed. Okay, you just try out a few examples with set.seed. Just try to pick some random numbers with set.seed, you will understand. Okay, so let's begin with today's topic, guys. So today we will be looking at inferential statistics. So we'll cover a lot of important theorems today. Okay, so let's begin with the first one, which is the first, not a theorem, this is not a theorem, which is called a z-score. So guys, were you able to answer the questions on GMAT which I had asked, where you had to find the area on the normal curve? That PPT, the questions which I sent out in a slide. Were you able to answer that? I sent out the solutions also, and I think the solutions were self-explanatory enough. You had to find the area on any one side or two side of the normal distribution. You could easily use the p norm function for that, right? All of you got it? A q norm, that was intentional. So I intentionally gave you another question which where you had to think differently, basically. So there, every time what I was asking you, every time I was asking you the area from the normal distribution curve, right, based on certain marks that you get. Now in the last question I reversed it. I gave you the marks, and I gave you the area, and I wanted you what marks will that be. So for that you had to use q norm. So all you had to do was Google. So you Google how to find uh, the 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 point which defines a certain area. That is what you had to find. Okay, or you could have used the R help page also. If you just write question mark R norm p norm, it will take you to a page which has q norm also given there. Neha, I think you can understand that yourself if you read. Okay, because if that way we go and discuss every questions, will it will take out all the times. So I request everybody to first at least make an effort to understand, because if we discuss things like this, it will eat away all of our time. Okay, but let's discuss anyways since you have asked. So let me open up the last one. So the question is, below what score do 95% of scores lie? Okay, the mean is 580, variance is, so what this means is, let me go back here. Okay, so this is your population, your mean is 580, your variance is 10,000, so you can just take the square root of variance to get your standard deviation. So your standard deviation is 100. Okay, 580 is your mean and your standard deviation is 100, and what you have to find is below what score do 95% of your scores lie. 95%. Okay, so you have to find a point here. Okay, you have to find that xi here, below which 95% of your scores lie. Okay, so this xi you have to find. So this area is 95%. This is 95%. Okay, so you can either solve it this way, or what you can do, if this is your 580, if this is 95%, this is 5%, or you can solve it this way also. So any one method you can take. So what you will do is, so let's say if I don't know the q norm function, I can still approximate it. Okay, I can see how do we approximate in this case. You already know that if you go two standard deviations from your mean, if you go two standard deviations away from your mean, how much do you get? You get around 95.5%, right? That's what you get. So that means these value, if you had gone 2 standard deviations from 580, which number will you reach at? You will reach at 580 plus 2 into 100. So 200. So you will reach at 780. So this means that if you reach at 780, you will get 95.5%, right? 95.5% is what you will get if you reach at 780. But the question is asking you not 95.5%, it is asking you 95%. So maybe a little bit less than here, right? Maybe I will be around 776 or 775. So this is how you can approximate the answer. Of course, we cannot get to the exact number using our hands. You will have to use software. But approximately it will be around 775 or 776. So between 775 to 780 is your answer. Now how do we find this? Then for that we can use the software. So let's say I'll just go to the help page of Pnorm. Sorry. So I go to the help page of Pnorm. And what do I find here? I find another function called qnorm. And see, qnorm has probability written into it. Okay. This is the only function which has probability inside. All others has x. So we were using pnorm till now, where we had to give the value of x. But now we want to find out the value of x given some probability. So that means qnorm function will be using. Okay. It also has similar syntax. The first input is the probability. Next you give the mean, then the standard deviation, and lower dot tail is true or false depending on what do you want. You want the lower side tail or you want the higher side tail. Okay. So we will be using this function now. So how we will use this is, I will write qnorm. Okay. So let's say I will follow the first approach. I'll follow this approach now to find the answer. Okay. So in this approach, I want the left hand side area, right? I want the left hand side area. So I will give 0.95. My mean is 580. My standard deviation is 100. And I want lower dot tail is equal to true. Okay. So see, the answer is 744. Okay. The answer is not close to what I had thought. Again, because it is non-linear, I made that mistake. So the answer should have been around 780, little bit less than 780. So I approximated this much, but actually it is non-linear, so it will be even less than that. So for 744 is the answer. Okay, for 95%. Okay, now let's take the other approach to do. Now let's take this approach. So this will also give you the same answer. Now same, I'll just copy paste. Here I will give 5%. So 0.05 I will give, and I will give lower dot tail is false. Okay. So see, this also gives me the same answer. So 744 is the marks below which you will have 95% of the students. Is that clear, Neha? And Saraswati, you must have gotten the same answer, right? Okay, I sent you the answers already. So if you open the solutions, this is what I would have done in the solutions. So 745 is the answer approximately. So question number 4, this one. Okay, so I have done the same thing. I have followed the first approach here. Okay, I have given both. What is 680? Jagdish, are you asking something? Okay, so Neha, is that clear now? Okay, so whenever you are asked a question like this, just draw a normal distribution and try to find that point. Okay, that is the easiest way to solve. Try to find the point which is asked and try to find the area on the left hand side or the right hand side depending upon the question. Okay, it is a pure geometry problem. Okay, so now let's come to today's topic, which is z-score. So what is z-score? Z-score is, you have already done it. So whatever example that we discussed now, that was nothing but in a way you were doing a z-test, or you were finding the z-score. Okay, so what is the z-score? So for any normal distribution, let's say this is your mean and this is your xi. Okay, so z-score is how many standard deviations away is xi from your mean. That is your z-score. Okay, so how many standard deviations away is xi from your mean? That number is your z-score. So how do you find that? How do you find how many standard deviations away is your xi? So it's very simple. You do xi minus x bar divided by the standard deviation. Okay, this will give you z-score. Okay, so if you just recollect whatever we discussed in the previous example, it was nothing but we were trying to find the z-score. So for example, in the previous question, what did I ask you? I gave you the mean of 580. Okay, and let's say I asked you how many students got 744 is what I had seen, right? So I asked you how many students got below 744. Okay, so here what you are doing is you are trying to find a z-score. So the calculation that the software does when you give that command is nothing but it first finds the z-score. So z-score in this case will be 744 minus 580 divided by the standard deviation, and you will get around 2 point, no, slightly less than 2 is what you will get. Okay, you will get around 1 point some 8 or 9, around this number you will get. So 744 minus 580, so you will get 1.64. 1.64. Okay, so this is how you find the z-score. Is that clear, guys? This is plain and simple, right? There's nothing much to understand here, just a simple formula. So now why is z-score so important? Why is z-score important? Because based on your z-score you can identify how far are you from your mean. Okay, in a normal distribution, for example, if this is your mean, so we have already seen that if you go one standard deviation away, you get around 68% of your population. If you go 2 standard deviation away, you get around 95.5%. If you go 3 standard deviations away, you get around 99.7% of your population. Okay, so this one standard deviation away is nothing but a z-score of 1. So this is nothing but a z-score of 1. This is a z-score of 2. This is a z-score of 3. Okay, so that means if your z-score is 1, what does it mean? And z-score, by the way, can be negative also. Okay, guys, so this means minus 1 to 1. This means minus 2 to 2. This means minus 3 to 3. Okay, so if this is your standard deviation and this is your mean, if you go 1 standard deviations ahead of your mean, then you will have a z-score of plus 1. If you go 2 standard deviations ahead of your mean, more than your mean, your z-score is plus 2, and similarly plus 3. Similarly, if you go 1 standard deviations below your mean, your z-score is minus 1. Okay, why minus? Of course, because your xi will become less than your mean, right? Because you are on the left hand side. So it will become this minus this will become negative because xi will become less than x bar. Are you following, guys? So you will have -1 here. Similarly, if you go 2 standard deviations, you will get -2. 3 standard deviations on the left hand side, you will get -3. So these are your z-scores. Okay. So the area between -1 and +1 is again 68%. This one. Similarly, area between -2 and +2 is your 95.5%. And finally, your area between -3 and +3 is almost 100%. Okay. So z-score is nothing but it measures how far from your mean are you situated, is your point located. So all these questions that we are discussing here, they all can be evaluated in terms of z-score. So for example, what is the probability that a randomly selected student score is at most 780? Okay, at most 780 means we are looking at the left hand side area. So 780, you can find the z-score of 780. So z-score will be 780 minus 580 divided by 100. So 200, so 2. The z-score is 2 in this case. Okay, so for the first question, the z-score is 2. At least 500. So 500 is less than 580. So that means your z-score will be negative. You are on the left hand side of your average. Okay, so if you go on the left hand side of your average, your z-score becomes negative. Okay, so this is your average, which is 580. So this is the second question. At least 500 means 500 will obviously be on the left hand side of 580. So here, so it's on the left hand side, so your z-score becomes negative. Okay, this side it's negative, this side it's positive. Okay guys, so that is your z-score. So just remember this definition. How many standard deviations away is your point from your mean? That is your z-score. Okay, now let's come to a very important theorem of statistics, which is called binomial theorem. Okay, which is binomial theorem. Now before I explain you the binomial theorem, let me ask you a small probability question. No, not this question. Okay, so this is a question. See if you can answer this, guys. So I roll a dice 5 times. Okay, I roll a dice 5 times. What is the probability of getting 3 sixes? Can you answer this question? Okay, Moinish says 0.6. What about the others? Okay. So Amit has gone into permutation combinations. Jagdish says 1 by 6 into 3 by 5. So 3 by 30. So 1 by 10 is what Jagdish says. Okay. So the answer to this is a little complicated than you think. Okay. Obviously it is not 0.6. Okay. Moinish, it cannot be 0.6. You cannot have more than 50% probability of getting 3 sixes when you roll a dice 5 times. Okay. 5 times 3 sixes is a lot, right? 3 sixes is a lot. So you cannot, if you have played any game with a dice, you will understand that this has very less chance. Okay, this has very less chance that you get 3 sixes in 5 rolls. So let's see how do we find this. Okay, so this can be done using binomial theorem. You cannot do it using normal probability. So whatever you guys are doing is not the way to approach this problem. So before I tell you what the theorem is, so obviously I cannot show you how to derive the theorem, but I'll just show you one intuition. Okay, so let's do one thing. Let's first try to find the probability of 1 6. Probability of getting 1 6 when you roll a dice 5 times. Okay, what is the probability of getting 1 6? Then we will try to find the probability of 2 6, then 3 6, then 4 sixes, and finally we'll find the probability of 5 sixes. Of course you cannot get more than 5 sixes because you are rolling it only 5 times. Okay, so what are the different probabilities, what are the different probabilities of getting the answer when you roll a dice? So you can get 6 numbers, right? You can get 1 2 3 4 5 and 6. These are the numbers that you can get when you roll a dice. You cannot get any number outside of this. Okay, so what are we interested in here? We are interested in sixes, right? We are interested in sixes. So what I will do is I will call getting a 6 as a success. Okay, I will call getting a 6 as a success for me because that's what I'm looking for, and all the remaining will be failure. Are you following, guys? I will call getting a 6 as a success, and all the remaining numbers will be failure for me because I'm not concerned with whether they are 1 2 3 4 or 5. I'm just concerned with whether they are a 6 or no. So 6 means a success for me. Any other number is a failure for me. So I'm not concerned with what that number is. Anything else is a failure for me. So I have divided my output into two classes, success and failure. That is why it is called binomial theorem. Bi means two. So are you following where I am trying to go? Why I have divided my output into two classes, success and failure? Because I am only concerned with the sixes. I am not concerned with any other number. So either I get a 6 or I don't get a 6. So yes or no, success and failure. Okay. So now let's see, if I roll a dice only once. These are the options I can have. Now in how many ways can I get 1 6? Okay. So I roll a dice 5 times. So 1, 2, 3, 4, 5. 5 times I have rolled my dice. Okay. What is the probability of getting a 6 when you roll a dice once? Okay, so this is first time when you are rolling, this is second time you are rolling, third, fourth, fifth time you are rolling your dice. This is third time, this is fourth time. So what is the probability of getting a 6 when you roll a dice only once? So this should be easy. When you roll a dice only once, what is the probability of this success? Yes, this is 1 by 6, right? Everybody understands this, right, guys? The probability of getting a 6 when you roll a dice once is 1 by 6 because there are total 6 numbers and the probability of any number will be 1 by 6, right? Everybody else, do you follow? The probability of getting 1 6 when you roll a dice once is 1 by 6. Okay, so I will write success here and remaining everything will be failure, let's say, and the probability of this success is 1 by 6. Okay, the probability of this success is 1 by 6. Okay, and what is the probability of this failure then? I'm talking about 1 6 only, right? So the moment I'll only write one success here. So what is the probability of failure? Yeah, of course it is 5 by 6. The probability of this failure is also 5 by 6. Of this one is also 5 by 6. Of this one is also 5 by 6. Okay. So the probability of getting one success in 5 rolls of a dice, what is it? If I ask you the probability of getting one success in 5 rolls of a dice, what I will do to these numbers? I will just multiply these numbers and I will get the final probability. Okay. I'll just multiply these numbers and that will give me the probability of getting 1 6 in 5 rolls of a dice. Okay. So the final probability will be 1 by 6 into 5 by 6 to the power 1, 2, 3, 4 to the power 4. So guys, did you follow how I got this? Anybody who has a doubt here? How did I get this number? This is the probability. Oops. So this is the probability of getting 1 6 when you roll a dice 5 times. Okay. This one. This is the probability of getting 1 6 when you roll a dice 5 times. Amit, because we are only concerned with 1 6, right? If I write another 6 here, that I will write in this case, not here. Because here I am concerned with only 1 6, not 2 6s. So I wrote it like this. Okay, those 2 6 scenario I will cover here, or 3 6 I will cover here. Here I am only concerned with 1 6. 1 by 6, Pankaj, because there are total 6 options to be taken, right? There are total 6 options. So it is 1 by 6. Or let me do one thing. I'll take a simpler example. Let me take tossing of a coin. Okay. So let me just save this page and let me open a new one. This is becoming a little complex. Maybe I should open a simpler example with, let's say, tossing a coin. Tossing a coin is easier to understand. And then I'll come back to the same example. Okay. Okay. Let's say this is a similar question, but now we are talking about tossing of a coin so that it becomes easier to understand. So we all know that probability of getting a head if you toss a coin once is 1 by 2. Probability of getting a tail is also 1 by 2, right? If you toss a coin once, everybody knows this. Now I'm tossing a coin 6 times. Okay, that means I have 6 places. So this is the answer that I get when I toss a coin the first time. This is the answer that I get when I toss the coin second time. This is the third time, fourth time, fifth time, sixth time. Right? This is the answer I will get. Now, since I am concerned with heads, I will define this as my probability of success. And this will be my probability of failure. So I will represent head as my success because I am concerned with my head. I will represent tails as my failure. Okay, so in this case both of them happen to be the same. So first let me start with a simpler one of getting all heads. Probability of getting all heads in 6 tosses. Okay, so that means I have 6 places here. Okay, all of them will be heads, so all of them I can write success, right guys? All of them will be heads, so all of them are successes. Now what is the probability of one success? So when you toss a coin once, what is the probability of head? Yeah, it's 1 by 2. When you toss the coin the second time, what is the probability of getting a head? Again it is 1 by 2, right? So all these probabilities are 1 by 2. All these probability of are 1 by 2. So now finally, what is the probability of getting 6 heads? What is the probability of getting 6 heads now? Yes guys, what is the probability of getting 6 heads? Yes, you will just multiply them. So 1 by 2 to the power 6. Okay, this is the probability of getting 6 heads when you toss a coin 6 times. And we see it makes sense also. So 1 by 2 to the power 6 will be a very small number. And we know that getting 6 heads when you toss a coin 6 times, the probability of that should be very small. We all know that. It cannot be large, right? You cannot win the toss 6 times in a row. Okay, so the probability will be very small. So this is the probability. Okay, now let's come to the second situation. Probability of getting 5 heads. Okay, now we will see the probability of getting 5 heads. So let me write it down: 1 2 3 4 5 6. So 6 times I am tossing my coin. 5 heads means I will write 5 successes: 1 2 3 4 5 success and 1 failure. Okay, so what is the probability of this success, guys? The first one, yeah, it is 1 by 2. Okay, again the probability of each success is 1 by 2. The probability of failure here also is 1 by 2. Okay, because the probability of tail is also the same. Okay, so here if I have to write the probability of 5 heads, the probability of 5 heads is 1 by 2 to the power 5 into 1 by 2 to the power 1. So I'm just writing it in a slightly different way. The answer is the same basically. Okay, the answer is the same as before. I'm writing it in a slightly different way. Okay, but again you can see that I can arrange this success in slightly different ways. So I can also write failure here and then 5 successes I can write. Right guys? I can represent it in this way also. This will be another way of getting 5 heads. Similarly, I can write 2 heads here, 3 heads here, then 1 failure, and then again 3 heads. Okay, so the same output can be shown using different ways. Okay, so can you find out in how many ways can you arrange 5 successes in total 6 places? Can you do that? Again, this is high school probability. Can you arrange 5 successes in 6 places? Saraswati says 5 factorial. 5 is a big number, Saraswati. 5 factorial. So 5 into 4, 20. 20 into 3, 60. 60 into 2, 120. So you are saying you can arrange in 120 ways 5 successes. Do you think that sounds correct? No, right? Not so many. It wouldn't be so many. So you have to arrange 5 successes in total 6 places. Yeah, how did you get that number? 30. Do you think it will be 30? Nope. Do you think you can arrange in 30 different ways? So the answer is, this is a typical permutation combination problem. The answer will be 6C5. Okay, so it is only 6 ways. You can only do it in 6 ways, not more than 6 ways. So it's easy. See, you can just find it here. So write success. So write 5 successes, then failure. Then write 1, 2, 3, 4 successes, then failure and success. Then write 3, write 2 here, 3 here. So these are the 6 ways you can do. There is no other way. Is there any other way, guys? You can arrange 5 successes in 6 places. These are the only 6 ways you can do. There is no other way. You cannot give me any other way of arranging 5 success in 6 places or 1 failure in 6 places. There is no other way. These are the only ways you can have. So the answer is 6. How did I get it? 6C5. So NCR, if you remember from high school, is the way of arranging R items in total n places. This is what NCR means. The number of ways of arranging R items in total n places. So here we have to arrange 5 items in total 6 places. So it should be 6C5 or NCR. Is this clear, guys? So on similar lines, I got 6C5. So what I will do, I will multiply this number by 6C5 because this is for one operation, for one way of arranging the probability is 1 by 2 to the power 5 into 1 by 2 to the power 1. Now this again I can do in 6C5 ways. So the final answer for probability of getting 5 heads in 6 tosses is 6C5 into 1 by 2 to the power 5 into 1 by 2 to the power 1. I'm just writing the answer in a slightly different way. Okay, so this is the probability of getting 5 heads in 6 tosses of a coin. So we have seen of the probability of getting all heads or 6 heads when you toss a coin 6 times. You have seen the probability of getting 5 heads when you toss a coin 6 times. Now similarly, let's see one more situation. The probability of getting 4 heads in 6 tosses. So guys, can you tell me what is the probability of this? 4 heads in 6 tosses. So looking at the above answer on similar lines, can you tell me? So again, I will not go into further derivation here. Tell me in this form. In this form, can you tell me? In this form. Yes, 6C4 into. So that is the total, Anand, that is the total number of ways you can arrange. That is the total number of ways you can arrange 4 heads or 4 successes in 6 places. But what is the probability of each? Yeah. So now it will be 1 by 2 to the power 4. Okay. Into again 1 by 2 to the power 2. Again, it is simple. Just look at this and change the numbers. Yeah, that is correct. Okay. So we will just look at this and change the numbers. So similarly, you can get for everything now. You can get for 3 heads in 6 tosses also. Okay. That will be 6C3 into 1 by 2 to the power 3. Again into 1 by 2 to the power 3. Okay. So what you have done is, without knowing, you have derived the binomial formula. Okay, without your knowledge, you have derived the binomial formula. Here, if I have to write it in a similar way, if I convert this, so this also was coming from the same formula. So I could have written this 6C6 1 by 2 to the power 6 into 1 by 2 to the power 0. Okay, just to convert it to the same formula. Okay, so all these formulas are the same. If I have to write it in terms of variables now, not with respect to this particular example, the formula will be NCR p to the power r 1 minus p to the power n minus r. This is your binomial formula. Okay. Now what is n? N is the total number of trials. In our case, n was the total number of times we were tossing the coin. Okay, that was our n. What is r? R is the number of successes that you are looking for. Okay, so we were looking for 5 or 4 heads in 5 tosses, in 6 tosses of coin. So 6 was your n. Since we are looking for 4 heads, r is equal to 4 for us. Okay, and what is p? P is probability of success in one trial. Okay, so in our previous example, our probability was 1 by 2. So 1 by 2 is the probability of getting a head if you toss a coin once. Okay, so that means P is probability of success in one trial. Okay, so once if you toss a coin, or once if you throw a dice, what is the probability of your success? That is your P. So we have seen what is n, we have seen what is r, we have seen what is P. So this is your binomial theorem. Okay, so we have, whatever we were doing here is nothing but we were using the binomial theorem without knowing it. So it has the same syntax if you see. Okay, so now if I ask you the question that we were discussing, that we started our discussion with, so you can use this. So find the probability of getting 4 sixes if you roll a dice 6 times. Now can you guys try to answer this? What will be the answer to this question? What is the probability of 4 sixes if you roll a dice 6 times? Now you can easily use this formula and come up with the answer. So just tell me the answer in the same form. I don't want the exact number as the answer. Tell me the answer in this particular, in the form of the binomial formula. Let's find out. Let's break it into smaller pieces. What is the probability of a success here? What is the probability of a success? If you roll a dice, what is the probability of your success? Now we are looking at sixes, okay? Okay, yeah, it is 1 by 6. Okay, so now you have given the answers itself. So let's see the answer. So of course, your probability of success is 1 by 6. What is your n? N is 6. What is your r? R is 4. Okay, so you have found your terms. Now you can easily compute the answer. So 6c4 into 1 by 6 to the power 4. This 4 will come here. Okay, if you see, this r goes here, into 5 by 6 to the power 2. This is your answer. Okay, so the answers which you gave at the beginning, it was not so simple. You can only use the binomial formula to calculate that. So 6c4 1 by 6 to the power 4 into 5 by 6 to the power 2 is the correct answer. Okay, so this is how you will use binomial theorem to answer questions like this. Again, all this may not be required when you do machine learning. You don't have to know all these theory, but if you know, you can appreciate the concepts better. That is why I cover these in my courses. You will not find any course on machine learning on any place covering all of this. Okay, maybe a course on statistics will cover this, but I try to cover this even in a machine learning course, so that you get a better feel of you will do, and later I will connect these dots. Where in machine learning these things will be applicable, I'll connect it later. Pankaj is asking, how do you calculate 6C4? Okay, so Pankaj, the way to calculate NCR is you will write n factorial divided by r factorial divided by n minus r factorial. So this is the formula to calculate. Okay, so if you have to calculate NC6C4, your answer will be 6 factorial, 4 factorial, 2 factorial. So 6 factorial, you can write 6 into 5 into 4 factorial. This is 4 factorial. 2 factorial is 2. These will cancel out. So 15 is your answer. Okay. So now let's come to assumptions of binomial theorem. Okay. Now let's come to assumptions of binomial theorem. So the first assumption is we deal in success and failure. Okay. It should be binomial in nature. It should be binomial in nature. So we are only dealing with success and failure. Okay. So that is the first assumption of binomial theorem. Okay, that we have seen already. The other assumption is that two trials should be independent. Any two trials should be independent of each other. So what do I mean by any two trials should be independent of each other? So let's say when you toss a coin multiple times, whatever output you get in your first toss never influences your output in the second toss. Right, guys? So if you win a toss once and you toss the coin again, whatever answer you got in the first toss will never influence what you will get in the second toss, right? If you got head in the first toss, that doesn't mean you will get again head, or that doesn't mean you will next time you will get a tail. So the events are independent, the trials are independent. Okay, so whatever output you get in one trial will never influence your output in the second trial or the following trials. So that is meant by two trials should be independent of each other. So that is a primary requirement if you want to apply your binomial theorem. So if you see the examples that we have discussed, tossing a coin is always independent. Your first toss never determines what you will get in the second toss, or never influences what you will get in the second toss. Similarly, rolling a dice is also pure random. What you get when you roll a dice first time will never influence what you get when you roll it again. Okay, so you'll have to be careful of these two assumptions when you run binomial theorem. That you only deal with success failure trials. That is why the name binomial, because success failure, two outcomes. The other is the trial should be independent of each other. Okay. So why did I cover binomial theorem? I covered binomial theorem. Yeah, we will come to that, Pankaj. So I'm basically building the foundation to finally come to the building part. Okay, this is the building part. Okay, so why did I cover binomial theorem for you? Because I wanted you to understand what is hypothesis testing. Okay, and this will be key to most machine learning algorithms. Okay, hypothesis testing is what will be key to your understanding of the machine learning algorithms. So let us see what is hypothesis testing. So do you want a break now so that you are fresh when we start with this topic? Okay, so let's take a break then, and then we will start with hypothesis testing. So it's 9:27 now. So let's be back by 9:40. Okay. Let's take a 13 minutes break. Okay. Okay guys, I'll see you again at 9:40 then. Okay, so let's continue. Sir, what did you see so far? So far we just saw what is binomial theorem. So the formula for binomial theorem is NCR p to the power r 1 minus p to the power n minus r. Okay, this is the formula for binomial theorem. You can use the binomial theorem when you have to find probabilities where the events are independent of each other. Okay, so any successive events or trials are independent of each other, and when you have only two outcomes, success and failure, that is when we can use the binomial theorem to calculate the probability. Okay, now this will help us to understand hypothesis testing. Now again, let me explain hypothesis testing using another example. Okay, so the example is this. So this is the question I ask. The question is, I toss a coin 20 times. Okay, I toss a coin 20 times and I get 17 heads. Now the question is the coin fair? Now I hope everybody understands what is a fair coin and what's an unfair coin. Okay, a fair coin is the coins that we usually see in circulation, which has a head and a tail. An unfair coin is a hypothetical concept. I am not sure if it exists. But in an unfair coin, the probability of any one of the head or tail will be larger than the other. It won't be 50-50. Okay, so maybe the probability of head might be 75% or 90% or whatever. Okay, so that's an unfair coin. So now this is the question we have here. I tossed the coin 20 times and I got 17 heads. Now the question I'm asking is the coin fair? So what will you say? Is the coin fair or is it unfair? Okay, Moinish says yes. No, I know, Anand, that we have to test this, but what does your gut feel say? What does your gut feel say? Is this fair or is this unfair? Okay, Deepayan says it's unfair. Moinish says it's fair. So Moines, when you say it's fair, that means you would have gotten this result if you did. So if you toss a coin 20 times, so take any coin that you have and you toss it 20 times, and if you get around 17 heads, that means it is fair. Is what you are saying. Yeah, we may get this result. Okay, Deepayan says that no, it is probably unfair. And no, Anand, it is not impossible. You can like what do you think? If you toss a coin 20 times, do you think you will get 17 heads? Yes, exactly. Yes, but very slim, right? You can get 20 heads also. Theoretically, if you say, you can get 20 heads also. But we know that we never get 20 heads if you toss a coin 20 times, right? Almost never. Yes, exactly. The pine is right. So the probability of getting 17 heads out of 20 is very less. Okay, in a fair coin. But right now you guys know the binomial theorem. So why don't you find the probability? You can calculate the probability exactly. So why don't you find the probability then? Because this is nothing but a binomial theorem problem, right? 20 times you are tossing, 17 heads you are looking for. So why don't you find the probability of getting 17 heads when you toss a coin 20 times? Okay, we will do that later, but let's start with hypothesis testing. So what is hypothesis testing? It is basically a concept which helps you find the answers in situations like this. Okay, so in situations like this, for example, I asked you, what is the coin fair? So the answer is yes or no. So in these situations, hypothesis testing will help you answer the question. Okay, so what do we do in hypothesis testing? We start with an assumption. Okay, we start with an assumption, and that assumption is called null hypothesis. So the assumption is called null hypothesis, or H naught. Okay, so we start with an assumption called null hypothesis, and the null assumption or the null hypothesis is usually the status quo. Okay, so status quo means uh, the most general occurrence. Okay, Pankaj, so hypothesis testing is a concept which helps you answer questions like this. Whenever you have a yes or a no question, a hypothesis testing concept helps you answer this question. So how do we do a hypothesis testing, or how do we test a hypothesis? We start with an assumption. Okay, we start with an assumption which is known as null hypothesis. Okay, or H naught, and very often or almost always your null assumption, your null hypothesis will be the status quo or the most general occurrence. So what is the most general occurrence? Do you see a fair coin or do you see an unfair coin in the most general occurrence? In the most general occurrence, what is a coin? A coin is fair, right? So in the most general occurrence, your assumption will be that the coin is fair. So this is my null hypothesis. My null hypothesis is that the coin is fair. Okay. So when the coin is fair, what is the probability of getting a head? If your coin is fair, since we are looking at heads, I'll be only considering head. If your coin is fair, what is the probability of head? It is 0.5, right? So your null hypothesis says that your probability of head is 0.5. Okay. So this is your null hypothesis. Now similar to null hypothesis and exactly opposite to this is your alternative hypothesis. Okay. So similar to your null hypothesis and opposite to this is your alternative hypothesis, represented by HA or H1 sometimes. Okay. So this is your alternative hypothesis. What is your alternative hypothesis? It is just the opposite of this. Okay, it will be exactly opposite of this. So here we said the coin is fair. So here we will say coin is unfair. Okay. So here we will say that the coin is unfair. So what happens when your coin is unfair? What will be your probability of head? If your coin is unfair, the probability of head will be greater than 0.5. 0. No, why 0? It cannot be 0, right? You got 17 heads. So it will be, yes, exactly. It will be greater than 0.5. No, because not 1. You cannot say 1. If your probability was 1, you would have gotten 20 heads, not 17 heads. That means it is slightly less than 1. That is why you are getting 17 heads. If it was exactly 1, you will always get head. You will never get tails. But here you got 3 tails. So that means it is slightly less than 1, but definitely greater than 0.5. Okay. So everybody understands this. Why have I written probability of head is greater than 0.5? Of course, you will never say it is less than 0.5, right? Because if probability of head was less than 0.5, you will never get 17 heads. You will get less than 10 heads in that case. But I have got 17 heads. That means the probability is greater than 0.5. Now, what is that exact value? We don't know. But it is definitely greater than 0.5. Okay, do you follow this, guys? Okay, now what we do in hypothesis testing, we find something called p-value. Okay, we will find something called p-value. This is capital P. Okay, this is not probability value. This is called p-value. This p stands for nothing basically. Okay, so what is this p-value? I'll write the definition first and then I'll explain. No, Deepan, it is not that. Okay, so what is p-value? We assume the null to be true. Okay, assuming the null to be true, we find the probability of the alternative or more in its direction. Okay, so this is a very important definition which I recommend all of you to remember this. Now you try to understand and remember, or you try to memorize and then you understand, that's up to you, but you should know this definition. It is asked a lot in interviews. It is very important to understand the concept of hypothesis testing. So a lot of people understand it and then they remember. A lot of people remember and then they understand. So it's up to you. Okay. So what does it mean is, in this example, you first assume your null to be true. Okay. So I have assumed the coin to be fair. Okay, so my probability is 0.5. That is the assumption. So assuming the null to be true, I will find the probability of the alternative or more in its direction. So what is the direction of alternative? Can somebody tell me what is the direction of alternative? So the direction of alternative I have given is probability of head is greater than 0.5. So what is the direction of alternative? I have already gotten 17 heads. I have already gotten 17 heads in 20 tosses. Okay, this is my outcome that I have got. Now what is the direction of alternative? Yes, the direction of alternative is towards 1. So when your probability of head is towards 1, what would the outcome be in that case? In Yeah, getting more positive or getting more heads, right, Arvind? That is what you mean, getting more heads, right? Yes, higher heads. So that means you will get 18 heads, or you will get 19 heads, or you will get 20 heads. You cannot get more than 20 heads because you are tossing it only 20 times. So this is the direction of alternative. Right, guys? Do you follow? This is the direction of alternative. Why? Because my alternative hypothesis says that the probability of head is greater than 0.5. So if your probability of head is greater than 0.5, of course you will be getting more and more heads. Okay? More and more heads is what you will be getting. So already you have got 17 heads. So the direction of alternative will be 18 heads, 19 heads, 20 head. Beyond 20 you cannot get. So that is your direction of alternative. Okay. So assuming my null to be true, we find the probability of the alternative or more in its direction. So now we have understood what is the direction of alternative. The direction of alternative is getting more and more heads. Okay, not below 17. Below 17, if you count, that will be opposite to the direction of alternative. Okay, your direction of alternative tells you that you will get more and more heads, not the other way around. Okay, if you get 15 heads or 14 heads, that is opposite to your direction of alternative. That is towards the direction of null hypothesis, not alternative hypothesis. Okay, so this p value is what we will find P-value is assuming P to be 0.5, we will find the probability of alternative or more in its direction. So what does it mean? We will find the probability of 17 heads. Okay, we will find the probability of 18 heads. We will find the probability of 19 heads, and we will find the probability of 20 heads. Okay, all of this when we toss 20 times. We will find these probabilities, we will add them up, and that is what is our p-value. Okay, the total probability of all of this will be our p-value. Okay, yeah Dipan, I'll explain it once again. So what did I do here is, I started with a null hypothesis. I started with a null assumption. The null assumption is that my coin is fair. So whatever is the status quo or the most general occurrence, that will be my null hypothesis. So I start with the assumption that my coin is fair. Okay. When my coin is fair, what happens to your probability? My probability will be 0.5. My probability of head will be 0.5, or the probability of success will be 0.5, because my coin is fair. Okay. Now the opposite assumption, the alternative assumption, is called the alternative hypothesis, which says that the probability is not equal to 0.5. So your coin is unfair. Your coin is unfair. Okay. So when your coin is unfair, what does it mean? It means that your probability is not 0.5. So that means it is either less than 0.5 or it is either greater than 0.5. Now less than 0.5 I am not taking, because I got 17 heads. Since I have gotten 17 heads, it doesn't make sense that the probability is less than 0.5. Because if your probability of head is less than 0.5, you will get less heads, not more heads. So I have already omitted that thing. So less than 0.5, it doesn't make sense given the question that is asked. So I have omitted this. Okay, I am only considering that the probability is greater than 0.5. Okay, now I come to a yes, Anand, we will answer that question. I haven't finished yet. Okay. So once this is complete, you will be able to answer that question. Is that coin fair or not? No, Ankit, the null hypothesis is always the status quo. So your status quo is always that the coin is fair. You never see a coin which is unfair, right? Do you? So your status quo is that the coin is fair. Okay. So now we will move to finding the p-value. So what is the p-value? The definition of p-value is that we assume the null hypothesis to be true. Okay, we assume the null to be true, and then we find the probability of the alternative or more in its direction. Okay, we assume the null to be true, and then we find the probability of alternative or more in the direction of alternative. Okay, so in this case we have realized, given the question that is asked, we have realized that the direction of alternative is getting 17 heads, 18 heads, 19 heads, or 20 heads. That is your direction of alternative. Okay, so now let us find the p-value, and then I'll try to answer the question that we started with. So to do this, we can use the binomial theorem now, which we have already learned. So to find 17 heads, the formula is 20 C17, 1 by 2 to the power 17, again 1 by 2 to the power 20 minus 17, right? So similarly you will run this formula for all 4 cases. So let us do that in R. So now we will learn how to run binomial theorem in R. Okay, it is very simple. Okay, to run binomial theorem in R, the formula is P binom. P binom is the function. Okay, P binom is the function. So what is the syntax? The syntax is that first you write the value of R. Okay, q is nothing but first you write the value of r, then you write the value of n, then you write the value of p, and then again you write whether you want the lower tail or the higher tail is equal to true or false. So this is the syntax of binomial theorem. Okay, so in our case I will use p binom. How many times am I tossing the coin? So I will start with 17 times. 20 is the total number of trials. Probability is 0.5 because I have assumed my null hypothesis. And my lower dot tail, since 17 is greater than the average, so the average number of heads that I would have gotten is 10, right? If I toss a coin 20 times, we usually expect to get 20 heads, but here I am getting 17, so the lower dot tail will be false. Okay, are you getting, guys? Oops. So this is the probability of getting 17 heads. Okay, everybody understood the syntax? This is the probability of getting 17 heads or more in its direction. So this I can show this the same Anand, the same as we have seen previously. So this is your normal distribution. You expect to get around 10 heads. I'm asking you what is the probability of getting 17 or more heads. So that means this side area. You need the area on this side. This is the direction of alternative, right? This is the direction of alternative. Okay. So that is why we covered all this before. So I will write P binom. I will give 17. Total number of trials is 20. Then I will give probability. The probability value is 0.5. And I will give lower dot tail is equal to false. If I give lower dot tail is equal to true, I will get the other side area. Now this is not the direction of alternative. This is the direction of null hypothesis. I don't want this. I want the other direction. So this shaded portion. Okay. So now you have gotten your p value and the answer is around 0.02%. Okay. So the answer is 0.02%. Very small. And we expected this, right? Of course, the probability of getting 17 heads when you toss a coin 20 times is very small. This never happens. It is almost impossible. Okay. So the probability of getting 17 heads or more heads if you toss a coin 20 times is 0.02%. So what do you think now? Is the coin fair or is the coin unfair? Yes, exactly. So coin is unfair, right? Because the probability of getting 17 heads or 18 heads or 19 heads or 20 heads is very small. It is only 0.02%. So of course the answer that you got, either you are lying that you got 17 heads or your assumption is wrong. Okay, so what was our assumption? Our assumption was that the coin is fair. Okay, so since your probability is very small, since your probability is only 0.02%, that means either the question is wrong. So this means two things: either you didn't get 17 heads. Okay, this is one outcome of this, or your assumption. So always remember that our assumption was that the coin is fair and then we got this probability, or your assumption that the coin is fair is wrong. Okay, so either of the two is true. But the first one is not wrong because I got this answer. I'm telling you that I got 17 heads. So this cannot be wrong because this is the question itself. You cannot say that the question is wrong. So this is correct. I know it. So of course this has to be wrong in that case. So your assumption is wrong. So your assumption that the coin is fair is wrong. Okay. So whatever assumption you started with is wrong. And what was the assumption we started with? We started with the assumption that the coin is fair. So your null hypothesis is wrong. That means the coin is unfair. Okay. That means that the coin is unfair. So if you have to just remember this small thing. P low, null go. Okay. P low, null go. So whenever P value is low, you reject the null hypothesis. You reject the null hypothesis. P high, null fly. Just memorize this kind of a poem. P low, null go. That means if your P value is low, you reject your null hypothesis. If your P value is high, you don't reject your null hypothesis, or you fail to reject your null hypothesis. Okay. So what is that P low means? Usually that value, the threshold is considered as 5%. If your P value is below 5%, you reject your null hypothesis. If your P value is above 5%, you don't reject your null hypothesis. Okay. So here we are getting a P value of only 0.02%. So that means we will reject our null hypothesis. What is our null hypothesis? Our null hypothesis is that the coin is fair. So we will reject that. That means the coin is not unfair. So we will reject the null hypothesis and we will go ahead with our alternative hypothesis. So null is rejected. That means alternative is correct. So that means our coin is not fair. So if you got this result, it means that the coin is not fair. Okay guys, did you follow? Point 0.5 Mohit. It should be 0.05, 5%. So 0.05. Okay. So let me give you another question. So you guys try to solve it yourself. Same, very similar. So again I toss a coin 20 times. Okay, I toss a coin 20 times. I get, let's say, 8 heads. I get 8 heads. And the same question, is the coin fair? So can you guys try to do this? So take out your notebook, write down your null hypothesis, write down your alternative hypothesis, then try to find your p value, and based on whatever you get in your p value, try to answer this question. Can you do this quickly guys? I'll wait for 2 minutes. So write down your null hypothesis, write down your alternative hypothesis, find your p value, and then based on p value you either reject your null hypothesis or you don't reject your null hypothesis. Okay, can you do this? You know the binomial theorem. You can use R to find the exact probability. So quickly do this. I'll wait. Then I'm sure it will be clear. Okay, Neha got 25%. Anybody else got the same answer? So that means that the probability of getting 8. Okay, so this question is a little tricky, okay guys. So think and do. It is on the other side. So the number of heads is 8. It is not above 10. So be careful of your alternative. What your alternative will be. Okay, let's see. Okay, so let me start with the null hypothesis. So what is your null hypothesis in this case? Again, your null hypothesis is that the coin is fair. That will remain the same. That doesn't change. So your null hypothesis is that your coin is fair. Okay. So my coin is fair is my null hypothesis. That means the probability of head is 0.5. Okay. So this is pretty simple. What is the alternative hypothesis now? Yes, guys. What will be the alternative hypothesis? You have got 8 heads out of 20. So what will be your alternative hypothesis? No, Jagdish, why 0.4? Where did you get that number 0.4? You cannot say it is 0.4 or zero point 0.3 or zero point 0.2. You cannot do that. Yeah, it should be less than 0.5. So the alternative is that probability of head is less than 0.5. Okay, that is the alternative. You cannot say that it is greater than 0.5 because you are getting less than 10 heads. Only if you get more than 10 heads, you will say that the probability is greater than 0.5. Okay, so your alternative will be that probability of head is less than 0.5, or you can say coin is unfair. Okay, or in another way you can say coin is biased towards tail, right? Because you are getting more tails, so you can say that the coin is biased towards tail. That is your alternative hypothesis. Okay, now our next task will be to find the p-value. So how will you find p-value? We will assume the null to be true, we'll assume the coin to be fair, and then we will try to find the probability of alternative or more in its direction. Okay, so we will try to find the probability of getting 8 heads or more in its direction. Now what is the direction of alternative, guys? What is the direction of alternative? Yes, yes, exactly, towards 0. Okay, yes, Jagdish, the direction of alternative is towards 0. So 10 is the mean. If your coin is fair and there is no randomness happening, you will get around 10 heads, right? If you toss it 20 times, 50% of the times you will get head, 50% of the times you will get tails. So 10 is what you will see here. Okay, so now our point is somewhere here, 8. So our direction of alternative is this direction, opposite of what we saw earlier. Okay, so this is the direction of alternative, HA. So now we will try to find the probability of getting 8 heads or less. Okay, 8 heads or less. So that means we will find the probability of 8 heads, 7 heads, 6 heads, all the way till 0 heads. Okay, all the way till 0 head is what we will find. So we can again use the p binom function. P binom, we will give 8, then we will give the total number, which is 20, then we will give the probability 0.5, and this time we want the left hand side area. So we will give lower dot tail is true. Okay, and how much do you get when you do this? 25%, right guys? This is what you get when you run this. Let me run it. So I'll just copy paste the same. P binom, this time it will be 8, 20.5, lower dot tail is true. Okay, so 25.2% approximately. So 25.2%. Now that's a lot of probability. That's very high for p value. So which one will you reject your null or will you not reject your null? So remember that poem again. P low null go, P high null fly. So our P is high, so our null will fly. Okay. So we can say that we fail to reject our null hypothesis. Okay. We don't reject our null hypothesis or we fail to reject our null hypothesis. And what was our null hypothesis? Our null hypothesis was that, so this is correct. This means it is correct. So that means the coin is fair. Now we cannot reject our null hypothesis. So our coin is fair. So your final answer is that your coin is fair. Okay. Is this clear, guys? Okay. Now we never say that we don't say that we accept our alternative. Okay. So when you fail to reject your null hypothesis or when you reject your null hypothesis, it is another way of saying that we are accepting our alternative. But that terminology is not used. We always say that we reject the null hypothesis or we fail to reject the null hypothesis. Okay, we never say that we accept the alternative hypothesis. That is not said. That terminology is not used. Why it is not used, I will give you an example for this. Okay, so hypothesis testing is what the judiciary of most of our countries, most democracies at least, work on. Okay, so let me give you one example which will make it clear. Okay, so the judicial system of most countries. So what does the judicial system say? If anybody has seen any movie, you will know. The judicial system says that you are innocent until proven guilty. Right, guys? This is what the judicial system says. It says that any accused is innocent until proven guilty. So the accused does not have to prove that he is innocent. It is the prosecution or the court which has to prove that he is guilty. The accused by default is innocent. The court has to prove that he is guilty. Okay, so what is the null hypothesis in that case? The null hypothesis is that accused is innocent. That is the null hypothesis. Okay, that the accused is innocent, and the alternative is that accused is guilty. So by default this is what will apply. Okay, and then what we do is we find the p value. Okay, what is the p value? We assume the accused to be innocent, and then find the probability of him committing the crime. Okay, then we find the probability. So assuming him to be innocent, so let's say somebody is involved in a accused of a murder. Okay, so what we will do, we will assume that that guy is innocent, and then we will find that, okay, if he is innocent, what is the probability of his being at the crime scene? Okay, what is the probability of his being at that situation, or what is the probability of the evidence against him? So let's say his hands were covered in blood. So what is the probability of his having his hands covered in blood? Of course, the probability will be very small, right? If your hands are covered in blood and there has been a murder, there is very little probability that your hands will suddenly out of luck get covered in blood, right? So that means you will reject your null hypothesis, so you are not innocent, that means. Okay, Pankaj has a question. Last example, we assume that we will get 1 to 8 heads. Yes, Pankaj? Not 1, 0 to 8 heads. 0 till 8 heads. Okay. Okay. So what do we do here? We find the p-value. We assume the accused to be innocent and then find the probability of him committing the crime. So this is where all the evidence will be presented, and the court will evaluate that what is the probability of the evidence against him. Okay, and then we find the p-value. If that p-value is low, if the probability is very low, we reject null. We reject null. If p is high, we fail to reject null. We fail to reject null. Okay, so let's say if we get probability high, if we get, let's say, 40% probability. Okay, our first case, let's see, we get a small p. We get a small p, let's say 2%. We get p value as 2%. What does that mean? That means that we will reject the null hypothesis, right? That means we will reject that the person is innocent. So we started with an assumption that the person was innocent, but we will reject that the person is innocent. So what will the court say? The court will say that the evidence against him doesn't say that he is innocent. Okay, that's what the court will say. The court will say that the evidence against him doesn't say that he is innocent, and the court will pronounce him innocent. Okay, on the other case, let's say you get 45% p-value. In that case, what will happen? You will fail to reject your null hypothesis. Yeah, whatever, it can be anything. It can be anything between 5 to 45 or 5 to 100%. Anything. Fine. Anything between 5 to 100%, if it comes, you will fail to reject null hypothesis. So, but always remember the terminology used. So why we are discussing this example? Just for the terminology. Okay. So whenever you fail to reject your null hypothesis, you will never say that he is guilty. Okay. The court will never say that he is guilty. If you read the court statement clearly, or if you have watched any movie, the court will never say that he is guilty. The court will say that the evidence, there is not enough evidence against him to say that he is innocent. There is not enough evidence to say that he is innocent. So given the evidence, he is considered to be guilty. So this is the exact statement which the court makes, that given the evidence, he is not innocent. The court will never say that he is guilty. The court will say that given the evidence, he is not innocent. Okay, so the terminology will be, you either reject the null hypothesis or you fail to reject the null hypothesis, but you never say that you accept the alternative. So you either reject that he is innocent or you fail to reject that he is innocent, but you never say that he is guilty. Given the evidence, there is not enough proof of him being innocent, or given the evidence, there is not enough proof of him being not innocent. That is what the court says in its written statement. It doesn't say that he is guilty or he is not guilty. Okay. So the judiciary system also follows a hypothesis testing. So any doubts, guys, in hypothesis testing? So again, this is the theory part of machine learning. Okay. Even if you don't know this, you can still do very good in machine learning, even if you don't know all of this. But if you know this, it's always good, right? You will do better in interviews. You will be able to appreciate your algorithms better. You will totally understand how an algorithm is working, so you will know all the maths behind it. So that is how it will help you. But even if you don't understand, you can still be very well off. A lot of people in the industry, they don't understand all of this because it's not required. Executing things is different than understanding the maths behind it. Yes. Okay. So this is all about hypothesis testing. Okay, guys. Okay. Now let's move to the next topic, which is again very important. So this is the central theorem of all of statistics, and hence it is known as central limit theorem. This is one of the most important theorems, not one of the, in fact, the most important theorem of all statistics. Okay. Uh, Pankaj, binomial is just a formula which is used to calculate your p-value. Okay, and that is not the only formula used. Okay, that is not the only formula that is used to calculate your p-value. There are other ways also you can calculate your p-value. It depends on your question. If your question involves success failure trials, then you will use the binomial theorem. But not in all cases you will have success failure trials, right? So another example. So if I have to give you another example, let me give you another example. So let's say I have a bag. Okay, I have a bag which has, let's say, 4 pink balls. I have a bag which has 4 pink balls, and it has 3 blue balls, and let's say 2 red balls. Okay, and I ask you a question. Let's say, what is the probability of getting 2 red balls in successive picks? Okay, so what is the probability of getting 2 red balls in successive picks? So you go on picking balls from here. What is the probability that continuously you get 2 red balls? So let's say you have 3 red balls. So now this is a question which cannot be solved using binomial theorem. Okay, you cannot use binomial theorem to solve this question. In this case, you use another theorem called hypergeometric. Again, this is not required for you. I am just telling you another case where binomial theorem will not work. So this is not a success failure trial. Okay, this is not a success failure trial. So here you will use another formula called hypergeometric formula to calculate your p, to calculate your probability. And similarly, if I ask you a question on this, if there is a hypothesis test involving this kind of a question, then your p-value will come from hypergeometric formula and not from binomial formula. So in that case, you will not use the binomial theorem. So my goal of explaining binomial was to explain you hypothesis testing. That is why I just took one of the formulas and I explained. We don't need to go into the details of all the formulas, how p-value is calculated and all, because anyways the software will do that for us. So just one of it, if you know, you will understand the concept. So understanding the concept is important, not going into the details of it. Yes, exactly. The only goal of taking you through binomial formula was to help you understand hypothesis testing. So if I just explained you hypothesis testing without covering the binomial theorem part, you will find the concept a little vague. You will not understand how is the probability coming. So that is why I covered also. Okay. So similarly, there are other ways also. There is something called chi-square test. Okay, chi-square test is also used to calculate your p-value. So chi-square we'll be looking at. So towards the end of the course, we will be covering chi-square test. Okay. So there are many ways you can calculate your p-value, not just binomial theorem. Binomial theorem is when you have a success failure case, a binomial case. Okay. Now let's come to central limit theorem. Okay. So first let me write the whole theory and then I'll explain. Okay. Okay, before I write down the theory part, so far whatever we have seen, we have seen most of the things following a normal distribution, right, guys? We have seen most of the things following a normal distribution. So all these concepts, binomial theorem, then we saw that if you go one standard deviation or when your z score is 1 on both sides, you get 68%. Then if you go two standard deviations on both sides, you get around 95%. And if you go three standard, you get around 99%. So all of this will work only if your distribution follows a normal distribution. Okay, only if your variable follows a normal distribution. So when I asked you this question, there is one important assumption here is, the important assumption is that the scores of the university entrance exam fits a normal distribution. If this was not the case, you could not use any of these formulas and you will not be able to calculate. Okay, if it was not following a normal distribution, calculating all of these will become next to impossible. Only if it follows a normal distribution you can apply all these formulas. Okay, this entire normal distribution assumption has to be there. Okay, so most of the concepts of statistics assumes that your data follows a normal distribution. Okay, it follows this kind of a distribution. Only then you can easily study this. Now, but that is you may wonder that that may not be the case, right? Why do we assume that your data follows a normal distribution? Why is that the case? It might not follow the normal distribution. So now we will see that why is that assumption not wrong? Why is that assumption not wrong that your variable follows a normal distribution? So we will see a theorem which basically will support the fact that whatever is your population, when you take a sample from your population, the sample almost always follows a normal distribution. Almost always follows a normal distribution. We will see it now. And I will show you the proof of this in R also. Okay. So let me write this down. So whatever the distribution of population, so whatever the distribution of population, if you take a large number of sample of size greater than 30 observations, the mean of the samples will follow a normal distribution. Okay, so this is what The theory says that whatever is the distribution, or this is what the central limit theorem says, okay, and this is very important. The central limit theorem says that whatever is the distribution of population, okay, it can be normal, it can be non-normal, okay, whatever the distribution of your population, if you take large number of samples from your population of size greater than 30 observation, okay, the mean of the samples will always follow a normal distribution. The mean of the samples will always follow a normal distribution. So let me explain this. So let's say this is your population, okay, let's say this is your population, and let's say this follows some distribution, some complex distribution. It follows a distribution like this, which is not normal, okay. So assume this is the salary of all software engineers in Bangalore, okay, all IT professionals in Bangalore. So you have thousands of individuals here. I have asked everybody their salaries. Everybody, each software professional, I asked them their income, and I drew a histogram. The histogram, let's say it looks like this. Okay, definitely this is not normal. The histogram looks like this. This is not normal. Now what I will do, I will take a large number of sample of size greater than 30 observation. Okay, so I will start sampling now. So what I will do, I will take a sample of, let's say, 50 people. I will take a sample of 50 people here. Okay, let's say these are 50 people I have included. Okay, greater than 30 is what I have to remember. So I will take a sample of greater than 50, or like greater than 30, 50 people. So I take these 50 people. Let's say this is my sample 1. Okay, I ask them, each of them, I ask them their individual salary. So there are 50 individuals here. I ask them their individual salary, and I calculate their mean. So mu1 is their mean, the mean salary, okay, the mean salary. Similarly, I go to my next sample. I take my next sample here. This is my sample 2. Again, this is also of size 50, let's say. So this is also of size 50, which has 50 individuals. Sample 2. I calculate the average of this sample also. Okay. Let's say the average salary in this sample is mu2. And similarly, I do it. Okay. I take a large number of samples. So I take S3, again some individuals, mu3, and dot dot. So let's say I take 100 samples. I take 100 samples. This is mu100. Okay. So I take 100 samples, each of size 50. So size is 50 for each of them. And I calculate their average, the average income in this sample. Now when I will plot a histogram of this average. Okay. Plot a histogram of all mu1 till mu100. Okay. If I plot a histogram of all of these mu's, I will find that it is normally distributed. That is for sure. This is what the central limit theorem says. See, initially the population was like this. The population was not normal. But when you took many different samples of size greater than 30, and when you plotted them on a histogram, you found that they were normally distributed. Okay. So that is why the normal distribution, it is so popular, because even if your population is not normal, the samples that you take will eventually become normal. The sample mean will eventually become normally distributed, even if your population is not normally distributed. So imagine your businesses, you might have your variable of any shape in your business, but what we actually study, we don't study all the variables. We study a sample from the total data that you have, and that sample usually follows a normal distribution. This is the central limit theorem, which is central to all of statistics. Yes, Ahana, we will come to why that 30 limit is there. Okay, we will come to that. Yes, Ankit, yes, these samples are independent of each other. These samples have to be independent of each other. Okay. Pankaj is asking, Okay, Ankit is asking, are these samples independent of each other? Yes, Ankit, that is correct. Pankaj is asking, is in this case, average may be different due to many reasons. Okay, but how can we say that mean will lead to normal distribution? It is like we are plotting mean of a group, not of a group, of 100 groups in this case. Since we have taken 100 samples, I am plotting the mean of 100 groups. Okay, now how do we get this? That is the theorem part. I will not go into the proof of the theorem. Okay, Pankaj, I will not go into the proof of the theorem, or even I don't know that how is that derived, but I will definitely show you the proof of this in R. So in R, what I will do, I will create a random population, and then I will try to take many samples from it, and then finally I will draw a histogram, and you will see that it looks like a normal distribution. So I will prove this in R, but not in the theoretical way. Okay, but you guys do understand, right? The concept, do you understand, right? So if you have a population which does not follow a normal distribution, okay, the population does not follow a normal distribution. So the income of all software professionals or all IT professionals in Bangalore does not follow a normal distribution. But when you take many samples from it, so let's say you go to each area in Bangalore and ask for the income. So you go to a very posh area where the income is a lot. Let's say you have an area where most politicians are staying. So of course the income will be a lot. Again, I'm going outside the IT professional part here, but their income will be a lot. Okay, so maybe they will fall somewhere here. The average of a posh area will be somewhere here. But again, there will be not a lot of posh area, right? Only a few will be posh areas, so the height will be very small. Similarly, you might go to a few non posh areas, okay, a few poor areas, let's say. So there also the height will not be a lot. Most areas will be the average areas, so the height will be a lot. And remember, height in a histogram is nothing but the count or the frequency. So the frequency will be higher for average areas, and that is why it will eventually become a normal distribution. So again, repeating what a central limit theorem says, a central limit theorem says that whatever be the distribution of population, if you take large number of samples from the population, you just have to make sure that the sample size is greater than 30. Okay, if you do that, if you take a large number of samples of size greater than 30 from your population, the average of the samples will always follow a normal distribution. This is a theorem. Okay, it will always do that. Now let us go to, yes Pankaj, that is correct. So now let's go to R, and we will look at the proof of central limit theorem. So the proof is this. Okay, so the first line, what am I doing? I'm just creating an empty vector. Okay, the name of the vector is mean underscore sample. It is an empty vector. So if I run this, I won't get anything because it's an empty vector right now. So mean underscore sample, if I run this, it will give me null because it's an empty vector. Now I first define my population. So you already know what this function does. Run if function, it creates random numbers from a uniform distribution. Okay, so I take 100,000 random numbers from a uniform distribution. So if I plot the population, of course it will not be normally distributed. So this is my population. Okay, so my population is this, which is uniformly distributed, not normally distributed. So just note that this is not normal. This is not at all normal. This is my population. Okay, my population is not normally distributed. Now what I will do, let's take 10,000 samples of size 100 from the above population. Trying to do now, I'm trying to take samples. As the central limit theorem says, you will have to take multiple samples, and you just have to make sure that the sample size is greater than 30. So what I have done here is I'm taking 10,000 samples from this population, and each sample is of size 100. So how will I do this? I will create a loop. Each sample is of size 80. So let's say I take 80. Okay. So you know the sample function now. You can make use of the sample function. So I will create a loop because I have to take samples multiple times, 100,000 times, 10,000 times I have to take the sample. So 10,000. So I will create a loop for this. So I'm using a for loop for I in 1 till 10,000. Okay. I have kept this sample function inside the loop. That means every time the loop runs, a sample will be taken. Okay. Sample first is the population. Population is coming from here. And then you have 100. So sample size is 100. Each sample size will be 100 and a total of 10,000 samples will be taken. After taking the sample, what am I doing? I am trying to find the average. I am just trying to find the average of it. So mean underscore sample. What am I trying to do? So I have taken this A vector here. Next I am finding the, okay, let me do it in smaller steps so that it is easier for you. So I'll do it in smaller steps. So AVG is nothing but mean of my sample. Okay. AVG is mean of my sample. And next what am I doing? I am just merging my AVG into that empty list that I had created. So I had created an empty list, right? So the purpose of this list was to store the average numbers from the sample. It will just store the average numbers from the sample. You follow, guys? So my mean sample will go on adding the average values from the sample to this vector. Okay, I don't have to print it. So let me run this now. So for the population, you have already seen the population looks like a uniform distribution, nowhere close to a normal distribution. Okay, now when I run this, I will get a vector called mean underscore sample, and that vector will have 10,000 values. Each 10,000 value will be the average of the mean of the sample, will be the average of the sample. Okay, and each sample size is 100. So let me run this. It might take a while because the loop will run 10,000 times. So it is still running. Okay, so I have run this now. Now what I will do, I will draw the histogram of my samples now. So mean underscore sample is the vector which has the average of each sample. Okay, so I will run the histogram of this now. So you see it is normally distributed. It became normally distributed. This is the histogram of the mean. So our population was not normally distributed, but when we took multiple samples from it and we plotted the average of each of the samples, it became normally distributed. So just read the codes once, guys. The codes is not difficult, very simple code, and try to understand. So tell me if you have any doubts, guys. Which line, define which line is that? Mean underscore sample, not clear to me. Which line? First one, that is just creating an empty vector. Define I'm creating an empty vector which will store my average values. So I have to create an empty vector which will store the average values of each of the sample. So see, I have just opened and closed it. That means it is an empty vector. So every time one sample is selected, the mean of that sample will be put in that vector. Okay, and then what am I doing here? Here I am trying to merge it with itself. I am trying to merge it with itself. So initially this value will be 0, right? There is no value here. So the first value will get inside mean sample. Second time mean sample will have that first value. The second value will get merged. Again the third value will get merged. And finally you will have a mean sample which will have 10,000 values. Each value representing the average of each sample. Okay, each value representing the average of each sample. Okay, Arvind is asking, can we run the loop for 50 times instead of 10,000? Yes, Arvind, you can do that. You can run it for 50 times, but then plotting a histogram will be difficult because you will have just 50 points. So with just 50 points, it is difficult to plot a histogram. So let me take just 50 points. If I take just 50 points, so it will run quickly, but your histogram will not look very perfect in that case. So see, your histogram is not looking perfect. Oops. Where is my R? See, now histogram it is difficult to identify whether it is normally distributed or not because I gave only 50. So you should select a large number here. That's what the theorem also says. The theorem also says that you pick a large number. So take a large number of samples, not just 10 samples or 15 samples. Okay. The larger you take, the better it is. The more closer you will go towards a histogram. So let's take 100 and see. So if you take 100 and run it, so right now it is like this. If I run it with 100, now it will be more closer to a normal. See, it has become more closer to a normal distribution. You make it 200 or let's say 300. This is your population. Now if you plot it, see, it is even more closer to a normal distribution. So as you go increasing this number, it will slowly move towards a normal distribution. Okay, so that's why I took a large number. So this is the proof of central limit theorem in R. Okay guys, so that is why you can safely assume that all your business variables, in most cases, not always of course, in most cases whenever we apply an algorithm, so most of the algorithms in statistics, at least the initial algorithms that we will see, so the first few algorithms that we will see is linear regression, logistic regression. So these algorithms, they assume that your variables are following normal distribution. So a lot of people wonder that how can we assume that the variable is following a normal distribution. You can safely assume because no matter what your population is, whenever you take a sample from it, the sample means always follow a normal distribution. Okay, the sample mean as well as the sample sum. So it is a sample sum also. Even if you had taken the sum of the sample, it would still have followed a normal distribution. Okay, so sample mean and sample sum, they follow a normal distribution. Now Sahana asked me, why is that number 30 taken? Sahana, that 30, it is an empirical number. Okay, there is no reason for that, but it has been found that if you take less than 30, then the theorem is not valid basically. If you take less than 30, your theorem might not be valid. Not always, but it may not be valid. Okay. So if your population is normal, okay, then you can take even less than 30. Even less than 30 is okay. Your sample sum or mean will still be normal. Okay. If your population is normal, then your sample will always be normal. Sample mean or sample sum is normal. But if your population is not normal, then greater than 30 is mandatory. Okay. Only then your sample sum and mean is normal. Okay. So this rule applies only if your population is not normal. If your population is normal, then there is no limit. You can take 10 also. 30 is minimum, 30 is not required. Yes, that's what, Sahana. If your population is also normal, then you can take even less than 30. But if your population is not normal, then you will have to take at least 30. Okay, because in that case, it will not follow a normal distribution. Okay, guys. So that is the central limit theorem. Now we have the central limit theorem proof I have already shown you. Just two small things I have. One is called a z-test and one is a t-test, and then we can conclude for today. Okay, z-test and t-test is also important. Let's first discuss what is z-test. So we already found out the value of z-score, right? At the beginning of today's class, we found that z-score is nothing but xi minus x bar divided by sigma. Okay, if this is your normal distribution, if this is your average, and let's say your x bar is here, so your z-score measures how far are you from the average in terms of standard deviation, or how many standard deviations away from the mean is your point xi. That is your z-score. Okay, so what is a z-test? A z-test also, so the z-score that you are getting is basically coming from a z-test. Okay, so the actual formula for a z-test is this. Okay, so z statistic, or you can say z-score, the actual formula for this is xi minus x bar divided by s to the power n. Okay, this is the actual formula. Now what is this s? S is your sample mean. Okay, s is your sample mean. What is n? N is your sample size. Okay, n is your sample size. X bar is your, sorry, s is your sample standard deviation. Okay, s is your sample standard deviation. X bar is your sample mean. Okay, and xi is the point in your question. So this is actually the formula for z-score. In our case, n was 1. That is why we directly wrote this. Okay, so this is the formula for z statistic, or z-score you can say. So this is nothing but a special case of z-score, where your number of your sample size is 1. So that is why you directly get, so this s becomes equal to your this. So this is for the population. Okay, this is for the population. Now what happens, sometimes you don't know the standard deviation of population. You don't know the standard deviation of population. When you don't know the standard deviation of population, you take the sample standard deviation. So s is the sample standard deviation. Okay, s is the sample standard deviation, and then you basically find this. You find this, whatever area you want to find, you can find using this. Okay, so this is the formula for your z test or z score, you can say. Okay guys, is this clear? Now let's come to t-test. Now what is a t-test? Now a t-test is used to compare the mean of two population. Okay, a t-test is used to compare the average of two population. So let's say you are a farmer. Okay, let's say you are a farmer and you want to test out a drug, a fertilizer. You have a fertilizer. Okay, you want to test if this fertilizer works and if it increases your crop production. So what do? You apply the fertilizer on half of your field. On half of your field you apply the fertilizer, on the other half you do not apply it. Okay, on the other half you do not apply it, and now you wait for a few months, and then once both of these crops they have yielded, now you want to check whether the part of land where you applied the fertilizer, has it yielded better than the other part. So you are trying to compare the mean of two population. This is your population 1, this is your other population. You want to compare whether this fertilizer helped you in increasing the yield or not. Did it help in increasing the yield or not? So you can do that using a t-test. So a t-test is used to compare the average of two population. So how do we do this? So let's say the yield, you take different samples. So to compare this, what you will do, you will take one sample here and one sample here. Okay, so let's say if it is, imagine these are all apple trees, for example. So you have 10 apple trees here, you have 10 apple trees here, or let's say 100 apple trees here, you have 100 apple trees here. So what you will do, you will pick some two trees here, you will pick two trees here, you will pick two trees here, and you will see which one yielded better. Let's say from these two trees you counted the number of apples you got here. So let's say you got, or let's say the weight of the apples, you got 100 kg apples from these two trees, and here you got, let's say 95 kg apple from these two trees. Now does it mean that your fertilizer worked? What do you say, guys? Does it mean that your fertilizer worked? You got 100 kg apple from these two trees where you applied fertilizer. You got 95 kg apple from the two trees from a farm where you did not apply the apple. So does it mean that your fertilizer worked? Yeah, you cannot decide honestly, because this might be random variation. This might be random fluctuation. Maybe the trees are small, they are not fully grown yet. So this is random, this can be random variation also. See, because each of these trees will have a standard deviation, right? Each of the trees will also have some standard deviation. They will not always be perfect, right? So let's say this is the normal distribution of all the trees that you kept fertilizers in. You gave fertilizer to all these trees. Similarly, this is the normal distribution of the trees where you did not apply fertilizer. So red means no fertilizer. Okay, and green means you applied fertilizer. So it can be something like this. So maybe you by chance got the best trees out of this, and by chance you got the worst trees out of this, right? So this is not, maybe not enough evidence. So this test basically can help you decide that. So what do? You basically find a ratio, you find a t value in that case, or a t statistic. you find a variable called the t statistics, which is nothing but your signal versus your noise. So what is signal? Signal means good information. Okay, good information versus your noise. Noise means the random variation. So if this value is greater than 1, that means probably your land with fertilizer did better. Okay, so how will you find the signal? We find the signal by just subtracting the mean. So mu1 minus mu2. So let's say this is mu1 and this is mu2. Okay, mu1 mu2 is the average yield of different samples that you have taken. So you cannot just take one sample and decide, right? You will take 2-3 samples. So let's say you have taken 4 samples here and you have taken 4 samples here also. Now each sample will have some average. Okay, the average quantity of apple produced in this sample, the average quantity in this sample. So all these numbers you have taken and you have taken their total average. So that total average is mu1. Similarly, the total average of all these samples is mu2. So mu1 minus mu2 divided by sigma 1 by n1 plus sigma 2 by n2 under root. Okay, sigma 1 square by n1 plus sigma 2 square by n2. This will give you your t value or t statistics. Okay, this will give you a t value. So this will be some number. Let's say you get 2.3. Okay, so this number will help you decide whether this particular land did better than the other land or not. Okay, now once you get this number, how will you decide? Again, you will go back to a hypothesis testing. You will again go back to a hypothesis test. So what you will do, your null hypothesis is that mu1 is equal to mu2. That means both the land, they do the same. So the fertilizer did not help. Okay, so your null hypothesis is that the fertilizer did not help. That means both the land will have the same average production. Okay, your alternative will be that land 1 did better than the other. Okay, that will be your alternative hypothesis, that land 1 will do better than the other. Amit, you have a question? Okay, so this is your alternative hypothesis. Now what you will do, you will again find your p value. So you will assume your null to be true and then find the probability of the alternative. So in this case, your p value will come from a t test. Okay, from a t test you will get your p value. So t test will give you this particular value, 2.3. Okay, so what will you do with this? 2.3 is not probability. Okay, this is the t score. This is your t score. So using this, what you will do now, you will go to a student t distribution. You will go to a similar to a normal distribution. So this is a normal distribution. Similar to that, you have another distribution called student t distribution. Now student t distribution is very similar to a normal distribution. Okay, so this is a student t distribution. It looks like this. Okay, now you will say that it is similar, it is same as normal distribution. No, it is not same. Normal distribution usually looks like this. It ends maybe after 3 standard deviation. After 3 standard deviations on both sides, your normal distribution will be almost done, right? We know that if you go 3 standard deviation on both sides, you get almost 99.7% of your data points. But in a student t distribution, it has longer tails. So it goes further. So you can go till maybe 5 or 6 standard deviations because it has longer tails. So its region is more. Okay, so that is the only difference between normal distribution and student t distribution. Okay, so you will take this 2.3 and you will plot it in case of a student tree distribution. So this is your student tree distribution, this is your average. So 2.3 positive means you will go on the right hand side, so 2.3 here. Okay, so this is 2.3 standard deviation. Okay, and then you will calculate the area on the right. If that area again is greater than 5%, you fail to reject your null hypothesis. If your area is less than 5%, you reject your null hypothesis. So you decide whether the fertilizer helped your land or it did not help. Okay, did you follow, guys? Questions, tell me. Guys, we'll extend the class by maybe 15 minutes. By 11:30 we'll be done. Okay. Yeah, 2.3 I just wrote. You will actually find it from the value of from this formula. You will find it. Okay, you will use that formula to find this formula. I just wrote some random number. You'll actually get the number using this formula. Okay, I know, guys, it was a little fast towards the end, but trust me, you watch the recordings. Okay, you will understand. So just remember, it is sometimes asked in interviews that what is t-test and where is it used. So in that case, you will be able to answer. A t-test is used to compare the mean of two population. So this is very common in healthcare industry, usually in healthcare. Okay, because in healthcare they test a lot of drugs. So how do they test a lot of drugs? So let's say you have a drug for headache or a painkiller. So how will they test? They check in this way. They will give the drug to a sample of population. So and the other half they won't give the drug. So there is a concept, something called A/B testing. Okay, so that is not a part of this course, but this is a very common strategy in marketing. Okay, what they do is they select a population and they do a A/B test on the population. So what is the A/B test? A/B test is where you divide your population or you divide your sample into two parts. One is called a control group and one is called a test group or a experiment group. So control group is where you don't do anything. You just control. You just leave it as it is. Okay. And the other is the test group where you give that drug. Whatever you want to test, you give that drug. Okay, and then you evaluate both the groups. So let's say you select 20 people. You select 20 people and all 20 are suffering from headache, let's say. Okay, to 10 of the people you give them the drug that you are testing. Okay, and to the other 10 people you just give them sugar pills. So you don't want there to be a psychological difference. Otherwise the people who did not get the drug might think psychologically, they might be feeling that we did not get a drug, so we will still have a headache. So what you will do, you will give them sugar pills. They will think that they are having a drug, but it will actually be sugar pill only. Okay, and the other group will actually get the drug. So 10 people will get a drug, 10 people won't get a drug. And let's say after an hour you will ask them, has your headache reduced or not? Okay, so then they will find out whether the drug actually worked or not. So this kind of a situation is called a A/B test. So you can google and learn more about it. Okay, this is very commonly used in marketing. Okay, so a t-test basically helps you collect the parameters from a A/B test and find it out whether the drug worked or not. Okay, so this is the formula that is used. You finally come up at your t-score. Using the t-score you calculate your probability, your p-value. You do that by using a t distribution, not a normal distribution. Okay, If it is a normal distribution, you will go to your z-test. But since this is not normal distribution, you cannot go to your z-test. You will use a t-test instead. Okay. So from a t-test, you will get your p-value. Once you get your p-value, you will go back to your null hypothesis, and you will either reject your null hypothesis or you will fail to reject your null hypothesis. And then you accordingly take a decision whether your drug helped or it did not help. Okay. So guys, I think I'm done for today. If you have any questions, you can ask, or we will do a quick revision. Okay. So let's do a quick revision, guys. We are already out of time. Okay. So we started with something called z-score. Okay. Z-score is very simple. It calculates how many standard deviations away from the average is your current point. Okay. So if this is your normal distribution, so z-test is always with respect to a normal distribution. Okay. If it is not normal distribution, you go to a t-test. For z-test means you can easily take the normal distribution. So the z-test measures how far from standard deviation is your point, how far from average is your point in terms of standard deviation. Okay. In terms of standard deviation, how far is your point? Is it 1 standard deviation away, 1.5 standard deviation away, or -1 standard deviation away? -1 means on the lower side. So this side it is negative, this side it is positive. Okay. So z-score measures that parameter. How many standard deviation away is your point from your average? Okay. So after z-score, we went to binomial theorem. Okay. Binomial theorem, we saw that the assumption excuse me, binomial theorem, we saw that the assumption was that your different trials should be independent. So each trial should be independent of the other. That was one of the assumption. And the other one was that the outcomes should be binomial in nature. It should be success failure trial. Okay. Only then you can go ahead with binomial theorem. So the formula we saw for that was NCR p to the power r 1 minus p to the power n minus r. This was the formula for binomial theorem, where n was the total number of trials. Okay. Total number of times you are tossing a coin, or total number of times you are rolling a dice, or so on. Okay. R is the number of successes you are looking for. Okay. So how many heads do you want, or how many sixes do you want? So that is your R. P is your probability of success in one trial. So what is the probability of head in case of tossing a coin, or what is the probability of getting a 6 in case of rolling a dice, and so on. So this gives you the formula. Using this formula, you can calculate the outcome of a binomial event. Any binomial event, if it is asked, you can calculate the probability of it. Okay. This is your binomial theorem. Next, we move to the central limit theorem, the most important theorem of statistics. So what does the central limit theorem says? Central limit theorem says that whatever be the distribution of your population. Okay. So whatever is the distribution of population, if you take many samples from your population, okay, if you take many samples from your population, and if you find, so you just have to make sure that each sample is greater than 30 individuals or items. Okay. You just have to make sure that each sample is greater than 30, and if you find the average of each sample, so mu1, mu2, mu3, mu4, mu5 and so on. If you find the average of each sample and then you draw a histogram of the averages. So this is all mu's together. If you draw a histogram of the average, the histogram will always look like a normal distribution. This will always be normal, irrespective of what the original population was. Even if the original population was not normally distributed, the average of each sample, so the sample mean or the sample sum also. So this is true for the sum also. Okay, the sample mean or the sample sum will always follow a normal distribution for all samples of size greater than 30. Okay, you just have to make sure that each sample is greater than 30 units. This is the central limit theorem. Okay, and we also saw hypothesis test. So hypothesis test is a concept which you use to basically come up with an outcome in case of an event, whether an assumption is correct or whether it is wrong. So you start by making a no Jagdish, each sample size can be different, but it has to be greater than 30. Okay, okay, next is your hypothesis testing. So what do? We start with a null hypothesis, we start with a null assumption, which is usually the status quo, and opposite of the null assumption we take the alternative hypothesis. Okay, and guys, some of you asked me, right, that why are we assuming that the coin is fair is null, and that the coin is unfair. So this is what we assumed, right? Coin is fair and coin is unfair. So some of you asked me, why did we assume this here? Actually, you can assume the opposite also. You can assume coin is unfair here, and you can assume alternative that the coin is fair. That is also possible, but then the calculation becomes difficult. But you can still do it. You can still do it. Theoretically it is allowed, but practically it becomes a little difficult to compute the p-values if you assume like this. So the calculations become difficult, but you can do it. It is not that you cannot do it. You can still do it. Okay, so to make the calculations easy, we assume that the coin is fair as your null hypothesis. Okay, so we assume that the coin is fair in this case. Okay, and in the other case we assume that it is greater than 0.5, or we assume that it is less than 0.5 depending upon the question. Sometimes what we do, guys, we also assume that it is just not equal to 0.5. This is also done. We are not sure whether it is greater than 0.5 or we are not sure that it is less than 0.5. We just assume that it is not equal to 0.5. In that case, what we do, so whatever we have done till now, we were calculating the area on one side of the normal distribution, right? Whatever we have done till now, we are calculating area on one side of the normal distribution, either this side or this side. So these are known as one-tailed tests. These are known as one-tailed test. When you give not equal to 0.5, you do something called a two-tailed test. There you find the area on both sides. So it is known as two-tailed test. Okay. Again, just remember these terms. If you want to study in details, if you want to go into the depth of statistics, then you might need all of this. But for machine learning, you don't have to go into that much depth. Okay. So knowing this is more than enough. So if you give an alternative hypothesis like this, you do something called a two-tailed test. Why two-tailed? Because you find the area on two sides, on both the sides. Okay, so it is a two-tailed test, and then you find your p-value. What is a p-value? P-value is assuming your null to be true. Assuming your null to be true, you find the probability of the alternative or more in its direction. Okay, you find the probability of the alternative or more in its direction, and then you calculate the probability, which is known as the p-value. Okay, so if your p-value is low, you reject your null hypothesis. If your p-value is high, you fail to reject your null hypothesis. Okay, you fail to reject your null hypothesis. Okay, and the threshold is usually 5%. Okay, the threshold is usually 5% or 0.05. Okay, so this is your hypothesis testing. Then we saw what is a z-test. Z-test is nothing but z-score you have seen already. Z-test is the same as that, but we use a z-test in case of when you take more than one sample. This is the formula to calculate your z-score. What we saw earlier was for where n is equal to 1, okay, and where you know the population standard deviation. Okay, when you know the population standard deviation, you can directly use that population standard deviation here. But when you don't know the population standard deviation, you use the sample standard deviation. So S is the sample standard deviation. Okay. Is there any cutoff to reject the null hypothesis? That's what the cutoff is, 5%. Dipayan. If your p-value is below 5%, you reject your null hypothesis. Okay. Yeah, I told that earlier, right? Okay, so this is your z-test. Now similar to a z-test you use when your data follows a normal distribution. Okay, when your data follows a normal distribution, you do a z-test. When it doesn't, you do something called t-test. So what is t-test? It is also used to calculate, to compare mean of two population. Okay, so the formula for this is we find the t-score. How do we find this? We subtract the average of the two population, of the two samples from the two population. We take sigma 1 square by n1 square plus sigma 2 square by n2, square root of this. This will be our t-score. We take this t-score and we plot it on a t-distribution. Okay, t-distribution is similar to a normal distribution, but it has longer tails. Okay, this is known as student t-distribution. Student t-distribution. Why student t-distribution? So this was basically founded by a scientist called Gosset. Okay, now Gosset did not want to use his own name. He did not want to use his own name to name this theorem, so he used a pseudonym. To do this. So that is student t. Okay, so once you find this t-score, you plot the t-score on a student t-distribution, and then you find the corresponding probability. That probability will be your p-score, p-value, and based on that p-value, you either reject your null or you fail to reject your null, and then you take a decision finally. Okay, so that's all I had for today, guys. Any doubts? I know it was a bit tough class, so for all the batches, this class is one of the toughest class. So don't be discouraged if you found the class to be very difficult. It is not only you. All the students, they find this class to be the most difficult of the entire all classes. I tried my best to make it very simple for you to understand. Please revise, please watch the recordings once again. I will share a few resources from outside my course. So from the internet, I will share a few other resources which will help you understand it. But don't worry a lot about these. Okay, even if you have even if you have 50 or 60% idea of what I talked about in today's class, that also will be enough for you. Okay, so that also will be enough. So don't worry a lot about this. Don't go after these concepts and delay your machine learning part. Okay, no Amit, these are just theory. There is no R part for it. This is just theoretical concept which will help you in your machine learning. There is no as such usage, direct usage of this. It will help you in your machine learning part. That's it. Later we will see why did I taught you all this. I will connect the dots when we jump to your machine learning algorithm. So next week we will be starting with our machine learning. There you will see where hypothesis test will come useful. Then you will understand that okay, this is why we learned hypothesis testing. But right now it is just a concept. Yeah, this class is important, guys. This class is important. So at least hypothesis test you should understand. Z test, T test, if you have a vague idea it is okay, but make sure you understand hypothesis testing. Okay, make sure you understand that. Sahana, sample size, no, it can be different also. That is not a big deal. I took it the same in our code because it is easy. I cannot change it, right? Because I have taken a loop. So I'll have to change it again and again. So that is why I took it as 80. But you can take a slightly different size also. You can take 80 and 90 in some cases, but it cannot be very different. Okay. Don't take very different sample sizes. Okay. And you can say, guys, this class is one of the classes which differentiates a software engineer from a machine learning engineer. Okay. Because coding part, a lot of people do well in coding part, but but not a lot of people understand these concepts. Okay. So try to understand these concepts. Coding part, software engineers also do very well in that. And this is the key differentiator for a machine learning engineer or for a data science guy. Okay. Okay, so